Hello everybody. Just a wee point about the forces and lifts, just to mention, because you've been working on the tutorial questions there on that sort of context. If it's a person standing on the scales, right, it's a similar situation to what we had with the Newton balance. It's just that the forces arise in a slightly different way. If you're looking at someone standing on a set of scales, the situation is actually quite complex, because you've got the earth pulling the person down. You have the scales then push the person back up again, and we'll talk about that in a wee minute. But you've then got the scales pushing down onto the floor, and then you've got the floor pushing the scales back up. So the whole situation is quite complex, and what you have to do is you have to separate out the objects that you want to focus on, and then draw your free body diagram, just like we did with the 2 kilogram mass yesterday. So if we just focus on the guy in the lift, right, and let's say the lift isn't moving for it to begin with, right, so if you're just standing on a set of scales, what happens is you've got a person who is at rest, so therefore the forces on the person are balanced. So you would have the weight of the person acting downwards. We'll just use the 80 kilograms that is used in question 2 in your booklet, and that gives us 784 newtons. So that's the weight of the person. So just like we saw with the Newton balance, in order for this person to be at rest, the forces acting on them need to be balanced. Okay, in other words, equal and opposite. So it's a Newton's first law situation here. So that would mean that you need a force from the scales. It's what's sometimes called a reaction force, and that reaction force would just be equal to the weight. Okay, so that's the normal situation when you step onto a set of scales. Okay, so the scales exert a force on you because you're exerting a force onto the scales. Okay, and that's actually Newton's third law that's causing that, but we're focusing on Newton's first law because Newton's first law applies to the guy himself because he's at rest. Right, so the forces on him must be balanced. Okay, so his weight is pulling him down, and then the reaction force from the scales is pulling him back up again. Okay, so the forces acting on him are balanced. So his weight pulling him down causes him to exert a force onto the scales, and then the reaction force to that is the scales push on him. So that's this force here. Okay, so if we can separate out the Newton's third law situation just now, because that makes things a bit more complicated, and just focus on what's happening to the guy in the lift. Right, so what happens if the lift then accelerates upwards like we saw in the last video tutorial? So in order for this person to accelerate upwards, what we would need, because this can't change, so this will never change, that's the weight of the person, we need this force to become greater than the weight. Okay, so that means that the reaction force that you're getting from the scales has to increase. Okay, now there is a Newton's third law pair of forces going on here. So if the reaction force from the scales has increased, it means that the force with which the person is pushing down on the scales also has to increase, right? And that gives a higher reading on the scales than what you would expect, because it's actually the force of you pushing down on the scales that produces the reading on the scales. That doesn't really matter for us. What's important is that this force, that's the reaction force of the scales pushing us up, or pushing the guy up, has to increase greater than the weight, because there's nothing else exerting the force on the man. So there's just the gravity, the earth pulling him down, and the reaction force from the scales that he's standing on pushing him up. So this has to increase in order to get him to accelerate. Alright, so everything's accelerating together, but the reason the lift accelerates is because the tension here becomes greater than the weight of the lift and the occupants inside it, which is pulling the lift down. So the tension here has to go above the weight, Same thing has to happen for the guy. His upwards force has to become greater than the downwards force that's acting on him. Okay, so just to consider an example of that, if this force here were to change to, let's make it 944 newtons, we could use that to work out the acceleration of the lift. Okay, so the working for this is similar to what we did yesterday. It's a Newton's second law situation because the lift is accelerating. We're trying to find out the acceleration of the lift. The way that we do that is we find the acceleration for the guy that's inside the lift, because we know about what's happening with him. We know his weight, right? And we also know the reaction force from the scales. So say he's in the lift. This is what I said, we would be able to do if we were able to get access to the Clavius and do the experiment. You would find that you can stand on a set of scales in the lift, but as the lift moves up, say from the ground floor, the reading on your scales would increase above what it normally would be. So the weight, your apparent weight, would become greater. Okay, the reading in the scales. Okay, that's just because the scales are pushing up on you a bit more. Okay, that also means you're pushing down a bit more in the scales, which is why the reading's changing. That doesn't matter what's happening in the scales, it's what happens to the guy that's important here. So the reading would go up, let's say to 944 newtons. So using Newton's second law, we'll just go through the working to try and find his acceleration, and by finding his acceleration we've got the acceleration of the elevator itself. Right guys, so I've done most of the working here. So it's a Newton's second law situation, because the lift and the guy inside, they're both accelerating. But what we already know is we know that the unbalanced force is going to come about because we've got an upwards force here which is greater than the downwards force. So to find that unbalanced force, we take the weight from the reaction force, which means there's an unbalanced force of 160 newtons. Pop that into our F equals ma Newton's second law formula. 160 for the unbalanced force. The mass of the guy is 80 kilograms. See, he's got it written on his shirt there. And we're trying to find the acceleration. So to finish off that working, then we would just divide both sides by 80. Okay, which means that we've got acceleration equals 160 over 80. Just swap left and right hand side now, and that gives us an acceleration of 2 meters per second squared. So that would be his acceleration, and in turn that would be the acceleration of the elevator itself. Okay, so that's the working when you apply it to a situation where it's a reaction force from something that you're standing on or that the object's resting on. In this case it's the guy in the lift, and it's the reaction force from the scales that he's standing on.